for MaxSAT, which is then the last talk for today before the reception. Please.
Okay, thank you. I want to first start by introducing the terms in the title, so that at least the title is understandable. This is work with Arianatan, who's unfortunately not here, and Stefan, who's here as well. So I think most people here know what MaxSAT is, but just let's quickly go over the definitions. We're given a set of hard clauses and a set of soft clauses. And the soft clauses usually have weights, or they can be unweighted, which means uniform weights. And we're looking for a solution that satisfies all the hard clauses. So the hard clauses alone are a satisfiability problem. And then we want to satisfy as many of the soft clauses as possible, in the sense that the summed weight of the satisfied soft clauses should be maximized, or the other way around, we want to minimize the cost. So we want to minimize the summed weight of the unsatisfied clauses. Or as in the talk before, we can see the soft clauses as a linear optimization goal. Very different views on the same topic. And what we were interested in finding a different approach for incomplete MaxSAT solving. So we want to have an anytime solver. We want to quickly have some solution that might not be optimal, and we want to continuously improve this. So whenever the user stops the solver, we have a solution. And this means that we have no guarantee of optimality. So even if we find the optimal solution, we might not know that it's optimal. So we really we try and try and try again until we are interrupted for some reason. And we want to do this with a method we call SAT-based local improvement, which we use quite often. So it's we define a structure for the problem that we can use for our solution. And so our basic idea is we want to use some complete solver inside our heuristic algorithm, or in this case, our anytime algorithm. And this usually requires a specific structure that can be used for the solver. And so we assume we have some suboptimal solution as an input. So there's some oracle that gives us some solution that we get as an input. And then we repeatedly use this structure we originally defined to find like a smaller part of the instance that is small enough so we can give it to a complete solver and get hopefully some better small solution. And then we have some mechanism that reintegrates this improved solution in our global solution. And with solver, I mean, so what we have looked at SAT solvers, MaxSAT solvers, PDF solvers, SMT solvers to the Boolean solvers, so this whole family of kind of SAT-related solvers. And we have used this for decision tree minimization, for Bayesian network structure learning, for graph decompositions, for Boolean circuit minimization, for graph colorings, and so on. So by now, it's a very, very widely applied technique, and I can really recommend anybody who wants an anytime algorithm for some optimization problem to kind of check out the related work. So just to make this very loaded previous slide more clear, so how does it work? We have an initial solution that we get in our SNIM algorithm, and then we do the 3 steps over and over. We extract some local instance that we pass to our solver, and either we find no improvement and we just try the next local instance, or we integrate the local solution and again start the loop all over again. And you see it's kind of an infinite loop, so we iterate until we are stopped. So how do we define a local instance in MaxSAT? And this is not our idea. This has been done before. I will come back to this. So we just look at the limited set of variables. So we divide our set of variables into fixed and free variables, and we say we cannot change the fixed variables in a local instance. And then we can basically, what we get from this are assumptions. So everybody who is familiar with assumptions, so we say the fixed variables are assumptions, which means we can immediately remove all the instances that are satisfied under the fixed variables from our instance. And we can remove the fixed variables from all the remaining clauses, because then they're falsified literals. And then we probably get some unit clauses, which we can use for unit propagation. And then the resulting clause, the resulting instance will be much smaller than the original one. And then we can give it to our MaxSAT solver to get an improved solution. And if we find an improved solution for this small instance, it's automatically together with the fixed variables an improved solution for the overall MaxSAT instance. And we repeat this until we are stopped for a timeout or a limited number of operations, or the user interrupts us. As a small example, so we have an initial assignment in the left upper corner, which sets all the variables except the last to false. We want to fix variables 2 and 4, which means the other ones are free. So so we first remove all the clauses that are satisfied. You see the gaps on the right-hand side, and then we remove all the falsified literals, which already means that our instance is quite a bit smaller. Then we have a unit class. So with unit propagation, we get a much, much smaller instance. And then if you look at the instance, we can set either v3 or v5 to true, but not both, which means that since v5 was already set to true in the initial assignment, we cannot really improve upon our solution in this case, but we could vary it. So it might have also benefit to just set v3 to true and see what happens in our algorithm further on. So this the structure we will use is the primal graph. So the primal graph has a vertex for each variable, and two vertices are connected if the associated variables occur in some clause together. Yeah, so we can see v1 occurs with all variables in some clause, but v4 only occurs with v1 and v2, so there is no edge to v5 and v3. So this basic idea has been done in a paper last year by Hickey and Bacchus. So they used an incomplete MaxSAT solver from the competition to get an initial solution. And then what they do to select the variables is they assign a weight to each variable that occurs in the soft clause. And the weight depends on if the soft clause is satisfied or not. And then they perform uniform weighted sampling to get the set of fixed variables. And then they reduce the instance as shown before and give it a MaxSAT solver. And they do this over and over again. And their experiments show that they can actually beat the best incomplete solver from the competition using this. And this is a very neat approach. Really liked it, and it's very closely related to SLIM. But we thought, okay, so because they don't assign any weight to variables that don't occur in soft clauses. So basically, apart from these variables, everything else is chosen randomly. And this kind of ignores a lot of information that you can get by the instance. And we thought, okay, if you can do this in a more structured way, maybe we can improve upon this method. And what I mean with structure, so here is the primal graph of a rather small instance. The brown vertices are fixed variables and the blue vertices are free variables. And you can see that kind of this is all over the place. Although you can see that the instance has a structure, the free variables are all over the place. And there's no discernible pattern behind it. So where we started from is, if you give me an assignment to a MaxSAT instance that I should improve, what I have to do is I have to satisfy an additional soft clause. There's no way around it. Okay, so we thought, okay, we start with some unsatisfied soft clauses under the assignment we already have, and we add variables from there because we have to flip some variables in unsatisfied soft clauses. So why not start there? But now if I set one of the variables as free, I don't know its value anymore because it's free. It can be changed. And we reflect this by removing these variables from all the clauses because we don't know the value anymore. And then we get more unsatisfied clauses because if the variable was used to satisfy the clause, suddenly the clause is unsatisfied. And then we add variables from these unsatisfied clauses to our free variables because we need to satisfy them as well to be able to satisfy the soft clause in the beginning. And we do this step over and over again, picking variables from unsatisfied clauses and then removing the free variables from all the other clauses until we hit some boundary because we don't want our new instance to be too big. And we want to have them very small so we can repeatedly call a MaxSAT solver on the small instance. And then implicitly, what this construction does, it explores the primal graph. Right? So we have the variables in the soft clauses are vertices. We add them, and then we look at the neighborhood of the vertices that we have in our free in the set of free variables. So here's an example. So now it's the same example as before, but I colored the clauses depending if they're satisfied in green or unsatisfied in red. And so we see that there's only one soft clause satisfied, so it's rather low score. But of course, all the hard clauses are satisfied. It's a feasible solution. So we pick a variable from a soft clause in the first step. We pick v1. We remove it from all the clauses, and now suddenly we have three unsatisfied hard clauses. Okay, we do the same thing again. We pick a variable from one of the unsatisfied hard clauses. Let's pick v2. Again, another unsatisfied clause. We pick another variable. Now almost all the hard clauses are unsatisfied. And now we say, okay, for some reason we want to stop with three free variables, and we stop, and we construct a local instance. So now v4 and v5 are fixed. So we remove all the satisfied clauses by the assignment to v4 and v5. which leaves these gaps, and we removed V4 and V5 from all clauses. So now we have a smaller instance. And since we have no unit clauses, unit propagation doesn't reduce this instance further. But we can quickly see that if we can actually set V2 and V3 to true in this smaller instance, and then together with V5, which is fixed, we would get an assignment with 3 satisfied soft clauses. So we can improve with this smaller instance. So the question is where we're successful. So the first question is, like, does this actually explore the structure better than the LNS approach? And if you look at this visualization, you see clearly, yes?
I guess I don't understand how you can have V1, V2, V3 in that example, because the first clause was that they have that at least one of them has to be false.
Sorry?
The first hard clause,
yeah,
and the soft clauses. I don't understand what you mean. I mean, if you have you haven't satisfied all 3 of the soft clauses. We're trying to get max.
No, this is the instance. So we like, because V4 and V5 are fixed, they're not anymore in the smaller instance. But these are the soft clauses of the local instance. So it's like we want to maximize the number of satisfied variables.
So it doesn't satisfy the first.
They don't want to satisfy all of them. One of them would be enough. Even if he satisfies one of these soft, it will be better than before. He doesn't want to satisfy all of them.
So we kind of assume we cannot satisfy all of them, because otherwise this would just be SAT. But we assume, okay, we cannot satisfy all. We just want to maximize the number of variables to satisfy.
But your soft clauses are unit?
Sorry? Yes, sorry, that was maybe important information. So these are like 5 unit clauses saying V1, V2, V3, V4, V5.
It's not the solution, it's just this is not showing you the solution. So you haven't set V1, V2, V3. It said that's what you're allowed to set now. You're allowed to set V1, V2, V3, and we're going to set it. We still have to have satisfied all the hard clauses. So you'll maybe set V2 and V3 to true and V1 to false, and then you get all the clauses.
So if you look at how our algorithm selects local instances, we can see we now clearly see the structure of the instance reflected in our selection. Particularly if we compare this step next to each other, we can see that while the left one on the LNS is rather random, like ours really kind of picks up on the clustering inside.
But why do you think it's better?
So the reason why we thought it's better.
The question was, I was asking, why is a more nicely looking picture on the right better than more messy picture on the left?
It's a nicer picture, right?
It's a very good question. So actually, like, just that it looks nicer, if you want to say it's not better. So the reason why we thought it would be better is because if you would do local search, you would like flip variables, and then you have like unsatisfied clauses. You have to flip in those clauses and so forth. And that's exactly what we're doing. But like, instead of like flipping just one variable, we kind of look at different branches all at once. And this kind of coincides with doing it this way. But like, if you do it just randomly all over the instance, you're never guaranteed that the variables that you select are actually in some way related, and not kind of the propagation is not blocked by variables you don't pick in the middle. So, and then with selecting this, you kind of guarantee that there's like some way this could propagate from one variable to the other if you change the value. So that is the idea why we looked at this. Does this make sense? So we wanted to check if this is actually better, if this performs better. So we set up some experiments, and we oriented our experiments around how the MaxSAT evaluation is done. So there, the scoring is you divide the best result by the sober result. So if you find the best result, you get 1 point, and the closer you get to 0, the worse is the result. So the original LNS implementation by Benke and Bacchus used MaxHS as a MaxSAT solver, so we use the same for better comparability. And so there are a lot of implementation details that kind of not in this talk, but we just used one configuration for all the experiments, so we're not cherry picking among different configurations. And the way we set this up is we take the best solver from the last year's MaxSAT evaluation, nu diabolo ls, and we let it run for a given timeout. But after an initial timeout, we pass the current solution to LNS into our implementation, and we let them run to the end, and then we check which of the solvers performed better. So we need an input solution that we get from this incomplete solver, but we also wanted to know, does it actually improve upon just running the solver to the end? And we chose like timeouts of 5 minutes because that's what the MaxSAT evaluation uses, and 30 minutes because we were interested in how does it behave if you let it run for longer. So this is the result for the unweighted instances. And then what you can see is that actually if you take the average score of all instances, then our implementation is a bit worse than the state-of-the-art solver, but it still beats LNS. But more interesting to me was that, okay, we can actually improve upon more instances. So it's just that on the instances where nu double LS is better, it's just scores way higher. So it's not clearly better, but there's a clear advantage on several instances. And then if you let it run for longer, this becomes even more pronounced, which is not surprising because at some point the incomplete solver will run out of things to look at, and then any change will probably perform better, but will perform significantly better than the LNS approach. So I would say from these results, clearly using a structured approach over just random has an advantage. Yeah, sorry.
Yes, one question. As best solution, you are using the best solution of these solvers, or you were incorporating the best solutions of all the solvers of the MaxSAT competition?
If I remember correctly, we used the best solution from our experiments and the best solution from the MaxSAT competition. So the overall minimum solution.
Okay, thank you.
Yes.
I'm just missing something. Why are there fewer improved in the 30 minutes?
Sorry. So if you look at this, so this initial timeout is 1 minute for the 5-minute timeout and 5 minutes for the 30-minute timeout. That's why. And then if you look at the weighted instances, kind of it's similar, but this difference between how many instances we can improve in comparison to the MaxSAT solver itself becomes even more pronounced. And also the difference in the average score between LNS and our implementation is also clearly better. So the conclusion, so what I wanted to show in this talk is just this general idea of this LNS approach in a structured manner is a promising way to look at it. There's a lot of potential for improvement. There are several implementation issues, for example, like passing the local instances to the MaxSAT solver is a performance bottleneck. There might be solver combinations that work better than what we used. We just tried to make it more as comparable to LNS as possible to just check if using a structured approach really improves. And then it was actually very hard to integrate a lot of the MaxSAT stuff, particularly the incomplete solvers. And I would say that probably because it's optimized for the competition, and competition setting is not the setting we really used. So I hope that there will be like I will hope more people pick up on this, use the solvers, and then there's a bit more encouragement to actually optimize the solvers to these use cases. Some interesting open questions is where like I talked to a few people here already, and then somebody said, can you put this into a MaxSAT solver directly? Like why wrap it around and they call it like this? Can you put this logic directly into a MaxSAT solver to get some improvements? An open question that we tried to find out, but we could not really figure out why and when does it work really well. So we looked at community structures, we didn't explain it. There are some instances we know you kind of need to look at the whole instance to find an improvement. There we cannot do well, but there seems to be something going on that we cannot pinpoint yet. And then, so we use the Primal Graph as a structure, but there are other structures you can use for such instances. And then I think an interesting way to go is like to ask, is there a better structure than what we used? So thank you for your attention.
Question from André.
So you're using a complete solver. So you're running an incomplete solver, and then inside your loop, you're using a complete solver. Is this because of the technical difficulties you mentioned?
In part, yes.
Yes.
So I spent like, there's some technical difficulties. Then the nice thing about MaxSAT is for a complete solver, it often gives you an suboptimal solution as well. So even if you kind of stop it, you often get a good solution that's not optimal anyway. So it's kind of not anytime, but often has anytime behavior. So it kind of worked well within our framework.
I would be interested to understand better why there are different, I mean, technical difficulties, right? Maybe.
Yeah, I would gladly talk to you about it.
Yeah, I have a question. So you probably saw that for complete solvers, there is this now tendency to run MIP solver as a kind of a pre-solver for 5 minutes and then run for whatever, like certain amount of time. And this really defines the winner for the competition. So I was wondering, as a sanity check, did you try to run MIP solver or our tools and see what the bound they will give you after the same timeout?
That would be interesting. Essentially, so what usually happens when you look at what does, so the MaxSAT solver for the subcalls usually returns very quickly. So they actually get a lot of MaxSAT calls going on. So the small instance we create are rather easy usually to the MaxSAT solver.
Oh. It's easy to find some solution, but it's not easy to find the optimal solution, right?
Yes, but
so you can
on the instances, it's not clear how far away we're from the optimal solution. We just know how far away we are from the best known solution. So
yeah, what I'm just saying is a sanity check, you can run Grobia or even skip and see in the same timeout what would be the upper bounds that it gives you. It will be alternative for the incomplete, right?
This might be a naive question, but there's some classical work on using randomized rounding for MaxSAT, right? With some probabilistic guarantees about how approximation guarantees about it, how close it can be to the optimum.
Okay.
So I'm just wondering, does it make sense to use some of that in your approach?
I would have to look at the work. I'm not that familiar with it.
Okay. Yeah, maybe we can discuss offline.
Yeah, very happy to.
Any other questions?
Would incremental MaxSAT solvers help?
Yes, I think incremental MaxSAT solvers would kind of alleviate the bottleneck of making this subcalls, because you would have to instantiate this over once and then pass your local instance assumptions basically.
Right.
But it would have been kind of unfair to compare that with the LNS approach where they didn't use it.
Oh, right. Well, it could be easily plugged in.
Yes.
About the rounding thing, I think they would not work as well as the. We tried something at some point for fun, and I would be pessimistic about it, but you can prove me wrong. I have a general comment, if I may. So, could we please start defining MaxSAT as just a linear objective function subject to a set of clauses? Just a suggestion, because that's how the solvers view the instances.
Yeah, but it's kind of it depends on like what people have heard before, right? Like if you I tried to put in all three definitions.
Yeah, but it's you notice that it's really cumbersome to talk about this. So, soft clauses, and there can be ways. Because the solvers don't really work like that. I agree with them.
I think if I'm also allowed to come, we discussed it with the Jeremias already. I think it depends on whether you want in a community like it, like you're not going to change how theoreticians talk about MaxSAT. That's just not going to happen. Okay. And so if you want them to understand your talk, then you have to go through these hoops probably. I guess but if you go to the SAT conference, I guess this is already like you get the definition. Okay, minimize this linear objective subject to this synapse.
It's not.
But it's like it's a matter of community.
Unfortunately.
Other philosophical remarks, protests?
Still, it was very practical.
Hey, so then I think let's thank André again. And now, hopefully, there should be some kind of reception. Let's go out and find out whether there's waiting for us.
Yes. I realized we're just there.
It was kind of last question. Yeah, no, but I guess sort of when they sit down there and then the first question is triggered. Okay, so